So let me just begin by telling everybody a few words about myself and my experience in working in STEM so far. I grew up in Beijing, China. So I came to the States for graduate school in '97. So really my bubble living in the States has always been in the university. I never stepped outside the university. My first stop in the US was really at University of Michigan. And it was really a true adventure from the very beginning. I landed in Detroit and realized the graduate student scheduled to pick me up from the airport, pick up the wrong girl. So then I end up, waiting at the airport for half a day until the guy finally realized he picked out the wrong person, and then it came back to the airport. So that's how my adventure in the States started. And, I spent 6 years at University of Michigan. I know some of you are considering going to graduate school. It might seem like a really long time to commit your life to pursue a PhD degree. I remember being a little scared when I watched the histogram chart in the physics department and saying, what is the average time of getting a PhD in experimental physics? But it actually turned out the 6 years just flew by. It didn't feel extremely long. Once you start getting to research and start to think about, set goals for yourself, time just flew by. So I really enjoy my time at Michigan. Not at the beginning, I have to say. It was lots of hurdles. Before studying foot in the lab at Michigan, I actually never been to a real research lab. So I think many of you are really ahead of me in terms of getting started with research as an undergraduate. And there weren't a lot of things to do at Michigan in the winter, so I end up starting to watch football. So I actually become quite a fan of American football. And Michigan has a great program. I'll just tell you how old I am. I watched Tom Brady play at college level when I was at Michigan. And he's an old man now, although still a legend and NSF. So after Michigan, I went to Colorado because my field of research used lasers, and Colorado has this research institute jointly between university and NIST, National Institute of Science and Technology. That's a really phenomenal place to do research in optical science. So I was there, and my time in Michigan were full of a lot of struggles with research because I'm just doing research for the first time. I didn't know how hard it can get. And after you survive the PhD, doing research become part of my lifestyle. And I worked very hard during the week at Colorado, but I also played a lot on the weekends. Colorado has 14ers. I hiked 15 of them. And I also skied in the winter. So I really enjoy my time in Colorado as a postdoc researcher. So starting about 2007, I came to UT to lead a research group. So this is a picture taken about 3 years ago. And quite a few people in this picture are actually undergraduate. So my group have supervised research for more than 50 undergraduate in my time at UT. So I really enjoy working with undergraduate. I find them bring a lot of energy and enthusiasm to our research program. And on a personal note, while I are always busy during the day teaching and doing research, I spent my evenings and the weekend chasing after my twins, and they've turned 10 years old now. So it's been a challenging year for them and us, managing the the COVID restriction, but we're surviving. Everyone is doing well, I think, overall. I would say, life is, I really enjoy my job as a university professor. Not only I get a lot of energy interacting with students at different levels, I also enjoy the perks that my research bring. This is about 3 summer ago, certainly before the pandemic. My summer started in Europe. I was invited to give lectures in Amsterdam. And after that, after spending about 10 days there, you know, I went to Berlin, where I actually spent 3 summer, you know, for a few weeks every summer. I have some close collaborator there. Spent a couple more weeks at Berlin. Then I made my way to a collaborator's lab, and that's located in this tiny island called Okinawa, halfway between Japan and Taiwan. It's a brand new institute with about 10-year-old history, with some really amazing facilities. And these are the buildings they built among the mountains to avoid destruction to the natural environment. They build bridges to connect the buildings. And these are actually inverted bridges. You know, the support structures are below the bridges to suspend it. So it's a wonderful place to be. After that, I also have a lot of collaborators in Taiwan. I just spent some time in Taiwan before, you know, dropping my kids off in Beijing with their grandparents. My summer usually is full of travels, and I really enjoyed that part of my work as well. So, you know, that's a brief, perhaps a short introduction for myself. And I also want to tell the students on the call, especially, you know, for a lot of hardcore science field, there's a perception that you can only exceed if you're just, you know, born to be a brilliant person. I have very different perception to that. You know, throughout my career, I've struggled. But the biggest struggle really started at graduate school. I'm a very late boomer in graduate school, and I constantly make mistakes in the laboratory. For a couple of years, I don't know if I was able to pull it through. I was told by people around me, I mean, I was making mistakes that no one else has ever made. They just didn't drop the adjective there. They just didn't say it's such a stupid mistake, but they were just basically telling me no one else has ever made those mistakes before. So it was a hard adjustment for many reasons, but I think especially for experimental science, I think that it actually requires many skills, and you're not going to be good at every one of those. And if you're good at some, and you can really build on your strengths, we should always work on things that we're a little weak. But you can really not only survive, but also thrive. You know, I really felt that, you know, my research career has been on a rise after, you know, in the recent years. After, again, my initial time at UT was quite a struggle as well. So I think it's important to give yourself some time to find your path, and not get discouraged just because a few people around you told you you weren't born brilliant to do the science you like to do. Okay, so I just want to stop here briefly and see if there's any questions. And I see there's some comments, and maybe there's a question in the chat box. I don't know whether.
Kelly said Tom Brady is the best.
Yeah,
just add in some character there.
Yeah, when I first come to UT, I was very torn. It was also a time that, you know, we have Vince Young at UT, and the UT and Michigan were constantly battling each other, you know, at the highest level. I think both programs are going through some struggles now. But, you know, it's an interesting, you know, hobby. I think most people are a little surprised when I tell them I enjoy watching football.
So I have a question in regards to just being an engineering brain. Sorry.
Yeah. So, you know, I actually, because my cursor is a laser pointer already, it's actually hard for me to switch between panels. And maybe Abby, can you help me to mediate the questions?
Yeah, Ava, can you ask your question again? And then Kelly, you can go after.
Okay, so just with the engineering type brain, I like to understand how things work and whatnot. And I was curious in how you got involved in physics and why you chose that path initially.
You know, I have to say initially it's more of an accident for me. You know, I was good at physics in high school, but not phenomenal, especially for experimental science. You know, I was a little clumsy, you know, to say the least. I would like drop things on my foot and you know, things like that. And I had a hard time, but my undergraduate degree was in physics and physics education. I studied in China at a time. There weren't that many freedom to choose majors, depends on the city I lived in. I was given a choice of study physics or political science at a university I want to get into. So I wanted to be a high school teacher, actually. That was my plan. That was my plan in high school. I wanted to be a high school teacher. And I chose this university. 1/3 of my classmates are still now a high school teacher, but it was a comprehensive university. So I was given some majors to choose from. There's it was a no-brainer for me to choose physics over political science. Just not a very political person. It's a bit of an accident. Even in graduate school, I changed a research group. I was okay in the courses, but again, some of my classmates were better than me. I couldn't decide whether I want to do theory or experiments. I just based my decision on a number of random factors. I just didn't like the idea of sitting in a chair all day long, and I just thought, okay, I'll try experiment, although I never really have any serious experience doing experiments. I think I didn't realize I have certain advantages. Let me just speak for being a woman. I think being a woman, we're actually often very good at observing things. I noticed some of my students will have trouble repeating an experiment. I never had that trouble, because I was paying attention to all the details. Right. So, I think that turned out to be a strength, especially at the time that I'm, working in the lab, putting all the pieces together. And then even at the faculty level, I find myself have some advantages compared to my colleagues. I had to discover those advantages. When I'm first here at UT as a faculty, I was frankly intimidated by all the famous people around me. I have a lot of famous colleagues at UT. And so I didn't feel like that I fit in at the beginning. So I'm the kind of person who's not born with loads of confidence. I actually need to work to earn that just for the benefit of myself.
Thanks, Dr. Lee. And you kind of touched on this a little bit, but Kelly had a question and asked if you would mind sharing if you had some sort of support when others were telling you that you kept making mistakes and you were struggling.
I think that this, I actually, when I was at Michigan, a lot of things was a big shocker. I actually went to a staff member a lot. Just someone like Risa and Abby. I would go to them, because I don't have any potential conflict with them. They're not the person who's giving me research assistant. And, I try to make connections with people around me, that people that I'm comfortable with. I think we all need that. And my graduate advisor was a very optimistic and upbeat and supportive person, although he's not always available. I think you would notice that when you go to graduate school or you're already working in a research group. And I wish I'm more available for my graduate students now. I'm sure my graduate students say the same thing about me now. So, I think another thing is it's a purely a stubbornness. I have trouble to stop something in the middle. Anything I started, I just want to see to the end of it. I think that persistence is far more important than any other, probably natural talent that people around me seem to have. Then I have to work harder to train myself to do it.
Thank you. I think that's the last question, but if someone else has one, you're free to ask.
Certainly friendship outside of physics was important. Other questions?
I don't know if you're going to discuss this later in your seminar or not, but the current research you're doing right now could be interesting to hear about.
Yeah, so I plan on give a bigger picture, and then I will talk about a few topics that we worked recently.
Sounds good, thank you. And then there's a question from Alex that asks, did you face any discrimination as a female in a male-dominated profession?
You know, I wouldn't say it's a conscientious discrimination. I think there is a inconvenience in networking sometimes, you know. So, you know, for example, I cannot drink any alcohol. You know, it just gave me headache for days. And after, you know, in a conference, a lot of time people will go to, you know, grab a drink after the talks. And usually I feel uncomfortable in those kind of social environment. You know, actually, science is very collaborative. There is an important social aspect to it. It's also taken me quite some time to get comfortable with it. It's a lot of work for me to socialize with people, I would say. You know, it's not, I like people in general, but I also like to be alone. You know, when I go to conference, I listen to talk for a whole day. I'm already a little tired. And then asking me to pick up additional energy to social with people, it's quite a bit of work for me. So I had to really work on that and or pace myself, you know, maybe socialize for 2 days out of the 5-day conference or something like that. Okay. Anyway, so I just want you to know that people are very different, diverse in many different ways. And I think it's okay. To just learn to be comfortable with your strengths and perhaps weakness, and work on your weakness maybe one at a time. Don't let it overwhelm you. Accept who you are as a person, and you know, just focus on the things you enjoy doing. And certainly don't let other people tell you what you're capable of doing. That some of us may just take a little longer time to get to the level that we're you know, accepted, respected. You know, I always took that as a given. It doesn't obsess me if people kind of not immediately give me respect. Well, it should be the case, but also I just accept that I need to work a little harder to earn that respect. And I just don't let that bother me. You know, I think one of the things I do is I was able to, you know, kind of, you know, put these kind of emotional, negative emotion side of things aside relatively quickly. You know, I do experience them, but I don't let them bother me for long. Maybe an evening, and that'll be it. Okay, so let me get started with the technical part. You know, I want to tell you a little bit about how quantum physics plays an essential role in our current information technology, and also to advance the information technology. I feel pretty confident that quantum physics will play a major role as well. So knowing that I have a pretty broad audience today, I want to just play this YouTube video for you, and I watched it many times. Okay, and I still don't mind watching it again. I'd like you to listen to some terminologies, and then I'll come back to these terminologies that are still core concept of my research. Okay, so probably need to get out of the presenter view for a second and get this. And people don't realize they live with the triumph of physics, quantum physics every day already. So let me bring that over.
And here we are,
sorry.
the granddaddy of all quantum weirdness.
So this video is going to talk about double slit experiment. And I have to say, it's my all-time favorite experiment in physics. It just has so many conceptual implications.
Infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay, so I hope you enjoyed that short video. You know, the critical words are wave function and particle wave duality. And then this experiment will work equally well. Instead of using single electron, you can do that with single photons. And measurement can perturb the quantum system. So these are the challenges that we deal with when we are trying to apply quantum mechanics and use it in information technology. So for those of you who want to study the subject more, or just are looking for some summer reading material, I recommend the code book, which it's written in a kind of like a historical novel, not novel, but with a lot of interesting historical stories about how the competition between coding information and decoding and coding information had determined many important events in history. For those of you who are not physics major, I highly recommend this book, Physics and Technology for Future Presidents. Don't we all wish our politicians understand science and better? And they're making policy impact our life. And yet many of them have no clue about what science and technology are capable of, how they're shaping our everyday life and the technology and over almost every aspect of our life. So, for example, I'm leading summer reading programs for high school students on these topics. And then even for engineering majors, there is a push from the National Science Foundation to teach more quantum mechanics. And as you'll see, it really is essential for understanding the current technology. Okay, so let me summarize what I consider the three major components for information technology. So first of all, we actually need to store information. And we actually store information currently in small magnetic domains. And these magnetic domains are already approaching the size of 10 nanometer. If we were to meet the demands of, just again, still exploding information storage need, we will need to find a way to build smaller domains, and then we'll run into problem with, can they be stable? Okay, so we're really running into some very hard technical challenges there. And then we need to process information. We encode information in 0, 1 in terms of the domain wall, the North Pole up or down, but now we need to process them. So we actually store information in magnetic material, but we process information using semiconductors and predominantly silicon. And people in the industry understand silicon as a material is approaching the end of the possibility of innovations. So we have some serious challenges there to keep going. And then we need to transfer information. So instead of, although satellite and wireless transfer take up majority of the news, we transfer information oftentimes, especially long distance across the ocean using optical fibers. We're literally encoding information in laser light and piping them through across the ocean using underground fiber cable networks. Actually, at the turn of the last century, people were building these microwave cables that transfer information across the globe. So this is an important part of how we transfer information. Information storage, as I'll come back to this towards the end because it touches on some more advanced topic. And in terms of the information processing, they're done by devices called transistors. The first generation of transistor, it was first invented at Bell Lab, and it looked like this. People like Texas like to say it looks like a longhorn, okay, with two horns sticking out. And here's a source and drain. And we're literally shuffling electrons between the source and drains. And now that channel length is already at 7 nanometer. And the blueprint for going 5 nanometer and 3 nanometer is already in the works. And think about it, an atom is about 0.3 nanometer large. And now with a 3 nanometer channel length, you don't have that many atoms in between anymore. You really run into a very deep quantum mechanical regime. And we know that the transistor density has followed what's called the Moore's law, meaning that the density doubled every 2 years for many years, and that's clearly coming to an end. Okay, so we need to think about What is the next step in innovation? And it turns out to process information, you only have to build two types of gates. So you build what's called a NOT gate, give you a bit of 0, you need to flip it to bit of 1, and now give you 2-bit, and this is a generic AND gate. The output of this gate would depend on the input. Only when both input is 1, you get output of 1. So it turns out no matter how complicated a computer algorithm is, it can be broken down into logic operation to just two types, single bit operation and 2-bit operation. And that's what when people work on quantum computer, they just worry about building quantum gate, either a single bit gates or a 2-bit gates. And then essentially they're done, but they need to keep on improving the performance of these gates. So, you know, even today, when we're moving thousands of electrons from the source to gain, when we do that, you still need to turn to quantum mechanics to explain why that electron shuffling is possible at all. It's actually overcoming some barrier, potential energy barrier that's higher than its kinetic energy. It would not have been possible if you only know Newton's law. It really requires the phenomena that's called the quantum tunneling. So it's deeply rooted in our current day technology. And finally, like I said, we transfer information through optical fibers. And there's this, there's these toy demonstrations, the light just bent with the fiber over a certain degree. And there's this very elaborate underground optical fiber networks that are transporting the majority of the information across the oceans. So that technology, of course, was not possible before laser was invented more than 50 years ago. Almost with every major invention, when they first come up, people never knew what to do with them. That also speaks to the importance of doing fundamental science. When we were discovering this knowledge, we don't have the prior knowledge what they're going to be useful for. Interestingly, when Faraday first explained to the Royal Society how to generate electricity, he was asked the same question: why is this useful? It just shows the limitation of our imagination, right? So, and then, let's take out the crystal ball and say what the future of information technology would rely on. And I'm pretty confident to say that we'll rely on a quantum leap. So what I mean by that is we need to build devices and technology that lead to smaller devices that operate faster and saves more energy. So the energy requirement for running electronics, for example, supercomputers, is enormous, right? You hear the news about Bitcoins and how the energy consumption is a huge concern. That's because in electronics, we're not managing the energy efficiently. There's a lot of energy that are simply getting wasted in the form of heat. And that heat, to use a terminology, is actually conducted by acoustic phonons in the materials. And we need to understand how to engineer phonon properties and to solve that problem from a very microscopic level. So in the physics department, we don't worry about what devices that Intel might build in 5 years or next year. We ask some very fundamental questions. We ask the question, what are the smallest objects that we can use to store information? And what is small amount of energy we can use to transfer information? The answer to what is small amount of light is really a single photon, okay? And then what limits how fast we can actually manipulate electrons, because we need to manipulate electron to achieve the information processing. So we want to know the ultimate speed limit that we can do the switching. So before I go there, I want to define in our world how small is considered small and how fast is considered fast. You take a big rubber ball, you make it smaller, you still have a rubber ball. But you go to some labs, on your campus or here at UT, you make what's called semiconductor quantum dots. Many of you may have seen this picture. You're simply changing the droplet of semiconductor from 6 nanometer to about 4.5 nanometer. By doing so, you're actually changing the light emission colors. And there are actually quantum dot TV being sold at Costco now. And they exactly use this technology of confining electrons and to change their property. This is what we call quantum engineering. We're literally squeezing the wave function of electrons. Okay, so besides just digging out material out of your backyard, actually silicon start from there. It comes from sand. The silicon processing technology start from distilling them from sand. You literally dig them out, okay? And now we can grow material. What we want to do is to, again, squeeze the electron wave functions. So instead of letting electron move in all three dimensions, we squeeze them into a two-dimensional slab, or we squeeze them to a one-dimensional line, or finally, in the example I showed you in the last slide, we squeeze them into a small, tiny box, okay? So when we do that, we're changing many properties. We're essentially changing the allowed electron energies for electron to occupy inside material. Then we change many of their fundamental properties by doing so. So in my group, we use lasers to probe materials. There are many different type of laser that we use in my laboratory. One type is an ultra-fast laser. We view them literally like a fast flashlight, and we use this very fast flashlight to capture electron motions. So how fast are they? They're just this blip pulse of laser light that lasts about 100 femtosecond. So a femtosecond is 10 to the minus 15 second. And in the ultra-fast frontier, people are pushing down to an attosecond. Okay, so that's 10 to the minus 18 second. So just to build some sense, intuition for you, when we say something is very fast, we say it happened in a heartbeat, right? A heartbeat is about a second. If you take that second divided by a femtosecond, that ratio is the time that dinosaurs roamed the earth, that's 65 million years ago, to a heartbeat, okay, to a second. And turn that into a ratio of length, and that's a ratio between the distance between the earth and sun and to the width of an ant's leg. So we're taking a very fast camera to follow electron motions in semiconductors. So in some cases, that's the type of experiment we're doing, because that would tell us ultimately how fast we can manipulate electrons to realize information processing. Okay, so and now let me talk about something we've been recently working on, not just us, many groups around the world, not just in physics, but in chemistry and engineering. We're working with a new type of material for information processing and potentially use them for single photon sources. And these materials starts with just what's called exfoliation. So these gentlemen here got Nobel Prize largely because of paper they published just 5 years ago. This is a record. No one wins the Nobel Prize after 5 years of their discovery. But just as a maybe a fun story, Guy was a guy who likes to break things in graduate school. His advisor told him he will be no good for anything. He just he discarded his advisor's critique and moved on. And he first got famous by floating frogs in his laboratory. He realized you can use magnet to float many things. You can float a frog, you can float a pizza, strawberry, you can look for YouTube videos. So he was having fun floating various stuff in his lab for a while. And then, they had a rule every Friday afternoon, they just try something funky in the lab. So at some point they decided to peel material using Scotch tape. Literally Scotch tape, 3M Scotch tape is fine for many materials, but you have to buy freshly made 3M Scotch tape, okay? Has to be made this year or something like that. So there's a lot of things to play, but of course people has, gone to try other things. What's amazing in their discovery report is actually many material can be created down to a single atomic level, the thickness, a single atomic layer thickness. This is a superconductor. This is a graphite, just the pencil you write, and you can create them into graphene. The newest discovery is you take two graphene, twist them, you can create many different material for phases. This is a very complicated formula and for high temperature superconductor. high temperature superconductors approaching transition temperature are 170 K. If we all move to the polar area, if the Earth doesn't keep warming, we might be able to operate superconductors there, okay, at room temperature. It just make the room temperature colder. Okay, so I'm going to talk about this material, mostly this class of material. They're semiconductors. And as you can see, because they're already down to a single unit cell thickness, we are literally operating the ultimate quantum limit in 2 dimensions. So the new trick is to take 2 of these materials and stack them on top of each other. Because the bonding between the layers so weak, you can either separate them with a Scotch tape. You can also just, casually rotate them. So when you rotate them, you create a checkerboard. So let me show you that checkerboard pattern here. So this is a image taken by tunneling electrons from a sharp tip. And this image basically says there are puddles of electrons that would tend to accumulate there. And that's because what we call the band gap modulation in this material. Okay, so what happens, you take 2 materials have slightly different band structure, lattice constant. And if at one position, if they're perfectly aligned, if at AA position, if they're perfectly aligned, when you shift over by 10, 15 unit cell, the bottom hexagonal is going to stick out in the top hexagonal. As you can see, there's just this gradual and periodic variation of how atoms are aligned. And if atoms are aligned differently from the top and bottom layer, their electrons interact differently. And then it creates these pockets where electrons tend to sit. So this is not an optical image, but this is how I imagine when photons, when they're emitted from this material, are actually located spatially. So we really have a situation, we have a regular checkerboard array of quantum dots. Basically, we're confining electron in all 3 dimensions. And it's my belief they're gonna emit 1 photon at a time, okay? No one has demonstrated that convincingly yet. And that's a topic that we're actively working on. So why is it useful to send 1 photon at a time? This will be an example. If I want to have an absolute secure conversation with Kelly, for example, I see Kelly's videos on. So I'm going to tell Kelly, I will send you 100 photons in the next minute. And if Kelly only received 30, that likely someone is listening to our conversation and taking out the photons, because you cannot split a single photon anymore. So this is a form of secure communication based on quantum mechanics. So this is what we like to do, is to generate photon on demand and make these photons indistinguishable from one another. So we're not there. Oftentimes we're doing these tasks with a 90% success rate, but perhaps for certain application, that's still not good enough. And by the way, there are commercial devices that people sell, and people have even done voting with single photon in small cities in Europe. Okay, and China has managed to send a satellite, quantum satellite, where they were communicating information at the single photon level and relayed by satellite. So this is an area that we actually have some catch up to do. So the current solid state single photon sources are typically based on defects, and these are different type of defects: defect in the solid state high gap material, defect in an atomically thin material, and defect by just decorating molecule on a carbon nanotube. And this is a different type of a quantum dot grow on a solid state substrate. So, but the problem, as you can see, all of this have the emitter at more or less random positions. And also the size of the quantum box, these bright dots are actually the image of the quantum dots. And the size and shape varies, leading to photon at different energies. And that would compromise the quality of the communication security. Okay, so perhaps these van der Waals material can be created to make a canvas. You start with a canvas that was regular modulated energy pockets, That could be really a new way to generate solid state single photon sources. Okay. So another thing we need to worry about is this light emitters are emitting light to all directions. We need to collect them efficiently. So when we target informations in current technology, we use antennas. So how do we build antennas that are compatible with these quantum emitters that are just tiny? The answer, some researchers are pursuing hint based on these color windows in churches, because it turns out they have a lot of metallic nanoparticle with size on the order of 20 nanometer, for example. And then again, tuning the size allow you to tune the scattering color. So we've been trying to build these nano antennas using a much more controlled way. So we assemble these nano antennas actually using an AFM. So this is where I wish I've learned more chemistry. You know, chemistry is really my weak subject growing up. And, my colleagues in chemistry can make some of this using their magic tricks, and we just assemble them using AFM. Typically, almost like using a robotic arm, assemble them. But we do have some, advantage of it. We can pick the particle we want to assemble ahead of time. So things are a little more uniform, and I can precisely control their configuration, the type of particle that I want to use. So we've been working on these materials, what's called the plasmonic antennas. We're now trying to combine these work that we've done a couple of years ago with the 2D material that we've been working on the last few years. So I see my time is, I don't have that much time left, but let me talk about information storage. Information storage technology has come a long way. 50 years ago, we'll be storing a megabyte of information in huge cabinets like this. Now you go to Costco, you buy a terabyte of storage space that fits in your palm. And that's because, we have learned how to make magnetic thin film, and that have these kind of small domains. The technology we have today is already amazing. What you have is a read head that are flowing above about 10 nanometers above these storage media. And this storage media is rotating at a high speed. It's to give an analogy that I heard people in industry say, the technology we have today is like flying a commercial jet a meter above the ground and count every grass. So this is already where we are. But that's still not good enough to meet the demands of all these TikTok videos or whatever video you're creating, So we need to further improve it. But when we make them smaller, atoms don't sit still. They have all these thermal motions, right? At some point, this thermal energy is going to be enough to flip the bit. And that's not acceptable, right? You don't want your bank account to flip in the wrong way, right? So we need to find that compromise. How do we make small things more stable? So physicists have some weird ideas. They're using what's called skyrmion. So these are the picture of skyrmion. So I think of them as bad hairs that cannot be combed down, like your dog has these two, right? And then basically these little arrows represent the spins of an electron. So they have to be arranged in a particular way that we call them topological. And topological object has some inherent property that's hard to change. For example, an apple has a different topology with a donut. Topology is a subject that just describe how things are connected in space, right? Donut has a hole, and apple hopefully doesn't. So these spin texture has a certain topological number describing whether they have, like a hole or not. And then we use that property to store information. Then we can make them smaller and yet stable. So that's one idea that people are trying, not just in my group, but more broadly, obviously. And then let me summarize what I've told you today. So we're working on new information technologies that are firmly grounded in quantum physics. So we're going beyond the magnetic domains to skyrmions. So things that have a strange twirl to their spin texture that are protected by property like topology. We want to be able to process information instead of using thousands of electrons at a time. We want to move to the limit that we can manipulate a few electrons at a time. We also want to control them at faster time scale. So we want to be able to control them at a level of 100 femtosecond. That's, as far as we can see, sets the limit how fast you can control them. And then we also want to be able to transfer, in some cases, communicate information instead of using wave in a classical way, but go to the limit of single photons. So these are the things that really is a global enterprise that scientists around the globe are collaborating and also competing at the same time. And then you're joining a center that's called the Material Research Science Engineering Center, because we firmly believe that material lies at the foundation of all innovations. Beyond, below every application, you have all these layers of technology, and everything is made of something. So we're trying to make innovation at the material level to improve technology that's built upon it. So that's it. That's what I have to tell you today. And I'm happy to answer more questions, and thank you very much for your attention.
Thanks, Dr. Lee. If you have any questions, just feel free to unmute yourself.
I had another question. It's less related to the research and more of just kind of time management and whatnot. Like, I've always known that I wanted to have children in the future, and I've also been interested in a PhD and a work life. And especially with you having twins, I can't even imagine balancing both of them. So just tip my hat off to you. But what have you found helped you a lot in being able to manage both your career and with your children and whatnot, that balance?
So I have to share with you, I certainly had my failures. My kids, my daughter was just a couple of days ago accusing me for being useless. I think I do outsource work. I have help at home. Just my work day is pretty rigid. I go home at a certain hour. All my colleagues knows not to bother me between 5 to 9. But then they start texting me after 9. They know my kids are in bed, and they starting to want my attention to certain things. So I think set some boundaries and train people around you to know that when you are not available is important. But I also think, life is full of compromises. We're not going to excel in everything. The time I spent with my children, I try to make it things that matters. Actually, I have a very supportive spouse. My husband's are the soccer dad. I'm not the soccer mom. He's the soccer dad. And, but I make all arrangement, right? I arrange their classes, and I set up play day. And when I'm with them, I try to be patient. I do the things my husband doesn't excel. I try to make up for the things he doesn't want to do. And it's always a struggle, and I always try to refine that balance from time to time. But I think of research as a competitive sports in some ways, right? Yeah. And then again, there's a amount that I'm willing to put in effort, but there's also place I'm going to draw a line, right? So I don't want to sacrifice my family life entirely for the sports I'm doing. I really think about research as my hobby. I told one of my some of the REU students in my group, I said, I as college professor, I consider myself paid to teach, but do research as my hobby. I don't want that to overrun my entire life. But I still very much enjoy this competitive sports. Yeah. I'll just see how far I can reach and be happy with that.
Thank you very much. That's really helpful.
Mm-hmm.
So I know you showed us all the video on the double slit experiments. So I just want to have to ask you, like, what is your opinion about like the interpretation of like the double slit? Like, do you really believe the interpretation? Are you like many worlds, or like the whole like waveguide things? Like, what is your opinion about like the measurement problem.
Right. So, the wave particle duality is actually very hard to explain, right? So basically, I think of them for the most part as two sides of a coin. In one experiment, the particle side manifests itself. In other experiment, it's the wave aspect manifests themselves. So in the vast majority of the time, you would never be able to need both interpretation to understand the experiment. Actually, up to until a couple of years ago, it was believed it's not even possible that you have both particle aspect and the wave aspect showing up in the same experiment. But researchers are pushing that boundary. Okay, so they're pushing that wave and particle duality boundaries, just like we've always been exploring the boundary between classical physics and quantum physics. A lot of phenomena in quantum physics can also be explained in a classical analogy, like oscillator models. Trevor, you worked a little bit about light matter interaction. Sometimes we can literally think about how light interact with electrons as they're shaking a particle that's suspended on a spring. Right.
Yeah.
So there's many things that I would also say our daily language just fails to explain quantum mechanics. We cannot put it in words in some ways. You also perhaps have read that Richard Feynman has famously said, everybody would have trouble with their interpretation of quantum mechanics. It's like rationalized quantum mechanics prediction in our brain using English or whatever language you speak, or Chinese, whatever language you speak. It's really hard to do because it's completely contradictory to our daily experience. So I think at some point, at least for me, as someone who kind of practiced quantum physics, I just accepted, here's this 5 hypotheses. They're going to give me prediction that'll work. I cannot think about electron as a particle. I have to think about them as an extensive electron cloud as a wave function, right? And then in certain experiment, I have to think about electrons able to split themselves. It's not so hard if you accept the wave function description. It's a spatial extended wave function to begin with anyway. And it just another hard part is a measurement, right? So if you perform a measurement, it says the electron is aware of it's being watched, it's going to behave differently. It's just a way to describe it in a kind of in a cute way. But what is really happening when you do a measurement, you always are interacting with that system. How do you do a measurement? You kind of have to hit the electron with a baseball bat or whatever. You're interacting with it. You shine laser on it. You actually are causing the electrons to make transitions in its allowed level, and you irreversibly change the state, right? So quantum mechanics is highly statistical, right? That's what causes Einstein to reject it. Philosophically, he famously said God doesn't play dice, right? But now we're perfectly happy to accept this statistical prediction, for how quantum system is going to behave. Of course, the challenge is how do we work with computer that has that intrinsic quantum statistic associated with it, right? That's why error correction code is very important when we're thinking about processing information with small quantum entity. The current technology already builds on quantum physics. It's just because we're kind of moving many electrons at the same time. We're already taking a statistical output of this many quantum system, behavior. So, but as we shrink it into a smaller number of quantum systems, what shall we accept? I'm not saying these a single electron or single photon device will replace everything that's on our table or in our daily life. It would never replace everything we have comfortably used every day, but there will be application where they will excel. The layer material, for example, it may seem very impractical to some of you who are practically minded, but actually in a company like Intel and Applied Material Devices, AMD, are actually investing in these materials. So for the reason that they're very thin and they don't have dangling bounds, meaning they don't have loose electrons that are not kind of confined or taken care of or disciplined. You don't want electron running crazy on your devices.
Okay, well, that is all the time that we have. Thank you again, Dr. Lee, for coming and presenting today. I thought it was a very interesting talk. And if everyone can join me in thanking Dr. Lee with either reactions or actually clapping,
Yeah.
that's really fine.
You're welcome. Thank you all.